Hey there, STEM students. This is Ms. Ruark. We are getting into the structure of the atom, which is going to help us determine how they bond and interact and all that good stuff. So let's go. Oh, that's going to be low. All right, metallic bonds. So before we get into anything else, I do need to talk about metallic bonds because we haven't spent a lot of time talking about them. So let's go ahead and talk about them real quick, and then we'll jump into the structure of the atom and how to write those structures. So metallic bonds are going to be bonds that happen between metal atoms, and with those metal atoms there is no transfer of electrons, there is no sharing of electrons. They actually well, they do kind of share. We could say they share, and they do transfer, but that's because there's what we like to call a sea of electrons. And that sea of electrons allows those valence electrons to move from cation to cation. So these electrons here, they're kind of free-floating, and they just kind of move from cation to cation, and they jump all over the place. And that's what those free-flowing electrons, that's what's allowing those metals to conduct electricity so well and to conduct that heat so well, because those free-flowing electrons. You have to have a movement of electrons in order to make something conduct electricity. So when you charge your phone, when you charge your battery, in order for that phone to work, there has to be that flow of electrons. And when the flow of electrons stops, that's when your battery is dead. Okay, alloys. So alloys are metals that have been combined together. They have metallic properties of, well, they have metallic properties, but they can't be found on the periodic table. And the reason for that is because they take two or more metals and they stick them together. Okay, so you have two types of alloys. You have interstitial alloys, which is when the small atoms fit into the holes in between the solvent metal atoms, and that would be an example of this one. You have those small metals that are fitting in between the larger ones. An example of that would be steel. A lot of times they use that to make it stronger. Okay? And then another example would, or another type would be the substitutional alloy, and that's where they actually replace the atoms of the other one, and an example of that is brass. Let's see what else we have. Oh, that's it. Okay, so let's get into Lewis structures. So for Lewis structures, we need to review a couple things. So molecular compounds. A molecule is a group of atoms that have been joined together by a covalent bonds. Okay, and remember that covalent bonding is when they share electrons between two or more non-metal atoms. Okay, why are they sharing? Because they want to satisfy the octet rule, which means they want to be just like the noble gases. Okay, so when we write our structure, our molecular formula, which is what you're all familiar with, C6H12O6, this would be the molecular formula. NH3, molecular formula, because you're showing the formula of the molecule. This represents how many atoms of each element are in the compound. Cannot be determined by the what we call the crisscross method. Can't do it that way. You can determine it by creating a structural or a Lewis formula, Lewis structure, and we do this to satisfy the octet rule. 8. Octet meaning 8. All right, so atoms still tend to attain the electron configuration for a noble gas by sharing their electrons, which means that they're all looking to get 8 valence electrons. What are valence electrons again? Outermost electrons. Okay, all of them except for, what are the two that cannot? Well, helium, because it only has 2, of course, right? Okay. All right, so when we write the Lewis structure or the structural formula for a compound, we're doing this to give a visual arrangement of the covalently bonded atoms using dashes to show or represent shared electrons, and to use dots to show unshared electrons. So for example, hydrogen. All right, this will be a super easy one, so I'm going to do it real quick and then jump into how to do them. All right, hydrogen has 1 valence electron, and we represent it like this. Well, what if we had 2 hydrogens that were to come together? I've shown you this before. Now let's see how we can make sense of this. Well, these 2 hydrogen atoms, in order to be happy, they have to have a full outer shell. Well, their outer shell, remember, they are in the 1s sublevel, and the s sublevel can only hold 2 maximum electrons. Yes, it all comes back. I know. You're thinking, oh my goodness, I thought we could forget this. No, we can't. It all comes back. Don't forget anything. It all comes back. Okay, so the most electrons that this can hold would be 2. Well, for hydrogen, it only has 1. And it needs to get another one. And, well, guess what? Helium's not going to share with it. And there are other elements that will share with it. But look, there's another hydrogen sitting here. So why not the two of them share and make themselves happy? So if we were to draw this, we would draw it as H dash H, because we're showing that there are 2 shared electrons right there. Okay. So let's make a little bit more sense of this. How are we going to draw them? Well, there are some steps that you need to follow. So in the steps, the first thing you want to do is count the total number of valence electrons for the compound. We don't care about any of the other ones right now. We just care about valence electrons. All right, arranging your atoms, you're going to do what we call the skeletal structure. Skeletal structure. Okay, so hydrogen is never in the middle. Ever. Atoms in the middle are generally those with the lowest electronegativity. Yes, that's why you had to learn that. Carbon atoms are always going to be in the middle, and the reason for that is because carbon atoms are divas, and they like to be the center of attention, right? Yeah. All right, and most structures are going to be extremely compact and symmetrical. So except for extremely long chain molecules, which we'll look at when we get into a little bit with organic and carbon bonding, but the rest, those will be long chain and they'll be long. But the rest of them are going to be compact and symmetrical. Also, another thing, what group is the highest electronegativity? The highest electronegativity is going to be the halogens. So do you think that they will ever be in the middle? Never. Okay, so halogens will never go in the middle either. All right, and then we're going to fill in electrons starting around the central atoms until all valence electrons have been used up. When you get them all used up, you want to draw lines or dashes to show your shared electrons and leave the unshared electrons as dots. All right, so for an example, here we have methane. Methane, you don't know what the formula for that is, but it is CH4. Methane is CH4, methane gas. All right, carbon has how many valence electrons? Well, if you look at your periodic table, you would say that carbon has 4 valence electrons. And there's only 1 carbon atom, so there are 4 total valence electrons. Well, hydrogen, each hydrogen has 1 valence electron, but there are 4 of them. So 4, and each bring 1 valence electron to our nice little valence electron party. And so we have a total of 8 valence electrons to play with at our valence electron party. All right, now we need to arrange our atoms. Hydrogen never goes in the middle. Carbon always goes in the middle. Makes it easy. So we put carbon in the middle. We put hydrogen around the outside. Okay, and when you draw your skeletal structure, go on ahead and draw your dashes in there because you're showing that there's a shared pair of electrons, shared pair of electrons, shared pair, shared pair. And a pair, how many is in a pair? A pair equals 2. So there are 2 here, 4, 6, 8. We have used all 8 valence electrons, and when I like to refer to this as our bank account. This is our valence electron account. And when our valence electron count gets to 0, then we're done. Make sure that everybody's happy. Hydrogen wants 2, hydrogen wants 2, hydrogen wants 2, hydrogen wants 2, and carbon wants 8. Everybody's happy. Yay! Okay, so you've got some practice ones on your paper. What I want you to do is I want you to pause this. I want you to come back and check and see how you did. Just try it. It's okay if you make a mistake right now. This is practice. All right, so hydrogen, there are 2 hydrogens, and each hydrogen brings 1 valence electron to our valence electron party. And oxygen, there's 1 oxygen, and each oxygen brings 6. So we have a grand total of 8 valence electrons again. That seems to be like, that number just comes back all the time, doesn't it? It does. All right, out of these 2, which one goes in the middle? Well, oxygen, because hydrogen never goes in the middle. And so we draw it like this. Now, here's another question that's going to come up. Can we draw it like this? Well, yeah, technically with this you can, because I haven't talked about Vesper. But I like to make them, remember, we like to make them symmetrical. Is that symmetrical? No. Okay. All right, so we've used 4 electrons, so we subtract that from our count. We still have 4 electrons to go. Hydrogen has 2. Oxygen has 4, 2, 4, and this hydrogen has 2. So hydrogen is happy. If you want to draw a happy face, draw a happy face. Yay! Hydrogen here is happy. Oxygen is sad. And why is oxygen sad? Because it only has 4 and it wants 4 more. Well, look, we have 4. Oh, so we're going to draw dots. 1, 2, 3, 4, and we're done. Now oxygen is happy. Why would we not draw an extra one on hydrogen? Because it's already happy. We don't want to give hydrogen any more. It becomes very angry. Okay, fluorine. There are 2 fluorine atoms. Each one has 7 valence electrons that they're bringing with them for a total of 14. All right, which one goes in the middle? Trick question. There's only 2. There is no middle. Okay, so we've got a fluorine and a fluorine attached to each other with 2 valence electrons, so we subtract those, which leaves us with 12. This fluorine has 2 and it wants 8, so how many more do we need to add to it? We need to add 6 more. This fluorine has 2, it wants 8, we need 6 more. We need to put a total of 12 more around. Oh, look, we have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And they're both happy. Happy faces. All right, on ammonium. Ammonium. That was bad. Ammonia. All right, nitrogen. There's 1 nitrogen, and it brings 5 valence electrons. There are 3 hydrogens, and each bring 1 for a total of 8 valence electrons. What goes in the middle? Nitrogen. All right, and then we put our hydrogens around. Now, I draw it like this. Some of you may draw it like this. And that's okay. Some of you may put it like this. That's okay. It's the same thing. It's okay. All right, we've used up 2, 4, 6. We've used up 6 valence electrons. We have 2 left. Hydrogen is happy. Hydrogen is happy. Hydrogen is happy. Nitrogen is sad. It has 2, 4, 6. It wants 8. So we're going to put those 2 there. And guess what? Everybody's happy. Yes, I know Pharrell's song is playing in my head right now. You don't want me to sing it, though. It would be bad. All right. Hopefully this is making some sense, and when you come to class, we're going to practice some more of this. Let's see what else we have. Oh, multiple bonds. Ooh. All right, there can be more than 1 shared pair of electrons between 2 atoms. A single bond is when you have 2 atoms held together by sharing 2 electrons, which would be 1 pair. A double bond is when they're sharing 4 electrons, which would be 2 pairs, and a triple bond would be when they're sharing 6 electrons, which would be 3 pairs. Double and triple bonds never form with hydrogen or halogens. Why? Because halogens only need 1 electron and hydrogen only needs 1 electron. All right, so when we draw a single bond, we just draw 1. When we draw a double bond, we draw 2. When we draw a triple bond, we would draw 3. Okay, an example of this one would be N2. See if you can do that one. Try it. An example of this one would be CO2. And an example of this one, we've done tons of these already. So, all right, why don't we just try those and bring them with you, and we'll do plenty of these in class. All right, what else? We have diatomic molecules. This is a pair of atoms in elemental form, not in compound form. They do not exist as individual atoms because they are highly reactive. And there are 3 ways to remember them, and you do need to remember them. You can remember them as Dr. Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Okay, you can also remember them as heck no, hydrogen, nitrogen, oxygen, and the halogens. That would be like a rock group, right? And then 7 diatomic molecules, because they do make a 7 on the periodic table. All right. I think that leaves us for now. I thought these were kind of funny, so I would put these up here with bonding. And I will see you in class.